5.6 Partial Fraction Decomposition. When you learned about fractions in elementary school, you were taught how to combine fractions by making sure they have the same denominator. Decomposing a fraction is the exact opposite process. If you have a rational expression or a fraction made up of polynomials, you can rewrite it as a sum of fractions whose denominators are made up of non-repeated or repeated linear and quadratic factors. Case 1. The denominator is a product of distinct or non-repeated linear factors. The partial fraction decomposition takes this form: some constant over the first factor plus another constant over the next factor, and so on. Number 1, find the partial fraction decomposition of 5x plus 7 over x cubed plus 2x squared minus x minus 2. Begin by factoring the denominator by grouping. This denominator has distinct, non-repeated linear factors, so the equivalent fractions will take the form a over x plus 2 plus another constant b over the next linear factor, x plus 1, plus another constant c over the final linear factor, x minus 1. Now we have a rational equation. To solve a rational equation, multiply both sides of the equation by the LCM, least common multiple, the denominator of the fraction we are decomposing. So we're going to multiply both sides of this equation by x plus 2 times x plus 1 times x minus 1. This leaves us with an equation without fractions. Expand the binomials on the right side. Now we need to group terms by variable. We could distribute a, b, and c, and then factor out x squared and x. But instead, I'm going to do both those steps at one time. A, b, and c are all being multiplied by x squared. B and 3 times c are both multiplied by x. And the non-variable terms are -1 times a, -2 times b, and 2 times c. Because this is an equation, the coefficients of each variable will be equal. If I add a 0x squared to the left side, the coefficient of x squared is 0. On the right side, the coefficient of x squared is a plus b plus c, meaning a plus b plus c is equal to 0. The coefficients of x are also equivalent, so b plus 3c equals 5. And the non-variable terms are also equivalent, so -a minus 2b plus 2c equals 7. Now we have a system of equations that we can solve to find a, b, and c. Use Gaussian elimination and then back substitute. So a is -1, b is -1, and c is 2. Therefore, our original fraction can be rewritten as a sum of these partial fractions: -1 over x plus 2, -1 over x plus 1, plus 2 over x minus 1. And that is your partial fraction decomposition. Case 2. The denominator is a product of linear factors, some of which are repeated. If you have a repeated linear factor, you must write a separate fraction to represent every power preceding and including the one represented in the rational expression. Number 2, find the partial fraction decomposition of x squared plus 1 over x times x minus 1 quantity cubed. This denominator has a linear factor x minus 1 that has multiplicity 3 is repeated 3 times. Our first partial fraction will be a over the first linear factor, x. Because x minus 1 quantity cubed is a linear factor with multiplicity 3, we need 3 partial fractions to represent this. So b over this quantity x minus 1, but to the power of 1, plus c over this quantity x minus 1, but this time to the power of 2, and then plus d over this repeated linear factor x minus 1, this time to the power of 3. Multiplied by the LCM, x times x minus 1 quantity cubed. Expand the polynomials on the right side. Remember that x minus 1 quantity cubed, you could use Pascal's triangle for. Everything on the right side is grouped by A, B, C, D. Now I want to group things by variable. Both a and b are multiplied by x cubed. The coefficients for x squared would be negative 3 times a minus 2 times b plus c. The coefficient for x will include 3 times a, 1 times b, negative 1 times c, and 1 times d. And there's only one term without a variable, negative a. This time I have a cubic polynomial, so I'll rewrite the left side as 0x cubed plus x squared plus 0x plus 1. Now I can create a system of equations with equivalent coefficients. The coefficients of x cubed are equivalent. A plus b equals 0. Negative 3a minus 2b plus c equals 1. 3a plus b minus c plus d equals 0. And negative a equals 1. I won't even need to do any sort of Gaussian elimination. I can simply solve for a and then back substitute. So the partial fraction decomposition for x squared plus 1 over x times x minus 1 quantity cubed is negative 1 over x plus 1 over x minus 1 plus 0 over x minus 1 quantity squared plus 2 over x minus 1 quantity cubed. Case 3. The denominator has irreducible quadratic factors, none of which is repeated. If the denominator has irreducible quadratic factors, meaning they can't be factored further, then your numerator must take the linear form ax plus b. Number 3, decompose 2x squared minus x plus 4 over x cubed plus 4x. Begin by factoring the denominator. The partial fraction decomposition for this will take the form a over the first linear factor x plus, and then x squared plus 4 cannot be factored further, but it's not a linear factor, it's a quadratic factor. So this quadratic factor will be the denominator of my second partial fraction, but the numerator for an irreducible quadratic factor must always take a linear form. So we'll use bx plus c since we already used a. Now solve the rational equation by multiplying both sides by the LCM. Regroup by x squared, x, and constants. And now create a system of equations based on the coefficients. Solve for a using the third equation and then plug it in to solve for b. So our partial fractions for this rational expression are 1 over x plus 1x minus 1. Case number 4. The denominator has a repeated irreducible quadratic factor. Just like when we had a repeated linear factor, we will need just as many partial fractions to represent the multiplicity of the repeated quadratic factor. And any time the denominator is a quadratic factor, your numerator should take a linear form. Number 4, write the form of the partial fraction decomposition of this fraction. First of all, we have a repeated linear factor, x cubed. So our first fraction will be a over x to the 1. Then we'll add b over x squared plus c over x cubed, representing each power up to 3. Now we have an irreducible quadratic factor, x squared plus x plus 1. So our numerator will be linear, dx plus e over this irreducible quadratic factor. And then we have a repeated irreducible quadratic factor. This quantity is cubed, so we'll need 3 fractions to represent each power up to 3. The numerator will be fx plus g over x squared plus 2 to the power of 1. We'll just keep going through the alphabet here, plus hx plus I over x squared plus 2 quantity squared plus jx plus k over x squared plus 2 quantity cubed. Wow, fortunately, they're not making us solve this. This is the form the partial fraction decomposition of this fraction takes. For number 5, notice that the degree of the numerator is greater than or equal to the degree of the denominator. That means this is an improper fraction, and we must use long division before decomposition. A. After long dividing, our fraction is equal to 2x plus our remainder of 5x plus 7 over our divisor x cubed plus 2x squared minus x minus 2. Now we can decompose this fraction. Oh wait, we already did that in number 1. Yay! So copying down the partial fraction decomposition, the partial fraction decomposition of this is 2x minus 1 over x plus 2 minus 1 over x plus 1 plus 2 over x minus 1. Decompose.